Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today, 9.1. That's right everybody, we are going back to trigonometry. So, Unit 9 is all about trigonometry, and this is where we expand on it just a little bit more than we did in geometry. However, this first lesson should be mostly review from geometry. So if you don't feel as comfortable with trig, hopefully after this lesson we'll feel a little bit better. Let's start off by talking about the basics. Trigonometry. When you see that word trigonometry, what we're really talking about is the relationship between different sides and different angles. For today, we're looking at it through the lens of a triangle. So let's say we've got this angle that's, I don't know, some degree measure. We don't know the exact measure, so we're going to call it theta. Theta is like x, but for angles. We can describe theta in a bunch of different ways, but we want to describe it based on the sides we have here. Right next to theta is a side that we call the adjacent side. Adjacent just means next to. You might see us abbreviate it as ADJ. Again, adjacent just means right next to the angle that you're looking at. Then we have the hypotenuse. The hypotenuse of a triangle is just the longest side. You might see us abbreviate this as HYP. Finally, the opposite side is the one that's on the other side from the angle. If you took a straight line through the triangle, you would get to the opposite side. We, of course, abbreviate that with OPP. Be very careful, as the most important thing for trigonometry is knowing what side is the adjacent, what side is the opposite, what side is the hypotenuse. We use 6 trigonometric functions to describe this. And I want to start off by talking about sine, which you might see abbreviated in your calculator as SIN. The sine of an angle is the opposite side length divided by the adjacent side length. What does that mean? Well, let's take a look at example 1. In example 1, it's asking us to evaluate the 6 trigonometric functions from the angle. In this case, if we wanted to figure out what the sine of theta is, it would equal the opposite side, which in this case, what's opposite to the angle is 12, divided by whatever the hypotenuse is. We'll talk about this problem in a second, but it would be 12 over whatever our hypotenuse is. So that's basically what we mean when we're talking about a ratio or a relation. The sine function is just a way of saying it's the opposite over hypotenuse. Cosine is similar, but not quite the same. We abbreviate it as COS, and the cosine of an angle is the adjacent side divided by its hypotenuse, as you can see down here. Then we have tangent. And this is the last of the 3 sort of original trigonometric functions. The tangent of an angle is equal to the opposite side length divided by the adjacent side length. So if we have a triangle, let's say we've got a triangle that has side lengths 3, 4, and 5. And let's call this angle theta, right here. Oops, sorry, you can't see that. In this, we could find a couple of different relations. First of all, the opposite side is 4, so I'm going to label this as O for opposite. The adjacent side is 3, so I'm going to label that A for adjacent. And our hypotenuse is 5, I'm going to label that H. So we could find a bunch of different relations. For this angle alone, as of right now, we know how to find 3 of them. We could say that the sine of this angle is Well, according to this table, it's the opposite divided by the hypotenuse. Well, the opposite side length is 4, and the hypotenuse is 5. So if the sine is opposite over hypotenuse, that just means it's 4 over 5. We could do also the cosine. So the cosine of this angle is the adjacent side divided by the hypotenuse. In this case, our adjacent side is 3, and our hypotenuse is 5, so it's 3/5. And for tangent, that one is opposite over adjacent. The opposite is 4, the adjacent is 3, so we would say the tan of this angle, or the tangent of this angle, is 4/3. These are just ways of writing out ratios. Now, that is a lot to remember, so allow me to give you a little bit of a shortcut. SOHCAHTOA. SOHCAHTOA is an abbreviation that we can use to help memorize the different functions. The S stands for sine, the C stands for cosine, and T stands for tangent. The letters that come after it relate to what the sine, cosine, and tangent are. So for instance, SOH, the SO, means that the sine of theta is O divided by H, opposite over hypotenuse, just like this little bit here. The CAH, the Ka part of SOHCAHTOA, stands for cosine of theta, is A is for adjacent, and H is for hypotenuse. So it's the adjacent divided by the hypotenuse. And last but not least, for TOA, that's the tangent of theta equals O divided by A, which is the opposite over adjacent. Just a neat way to memorize it. These are what we've learned in geometry already, so none of this should be new. However, there are 3 more trig functions that we are going to be seeing. This is something that is new. They are called cosecant, which is abbreviated as CSC, secant, which is abbreviated as SEC, and cotangent, abbreviated as COT. These 3 functions are related to the ones above them. So sine and cosecant are related, cosine and secant are related, tangent and cotangent are related. But how are they related? They are reciprocals. Reciprocals just meaning flipped versions of the originals. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. It's like we just flipped the fraction. Same with cosine and secant, as well as tangent and cotangent. We're just flipping the fractions. Before we go into this, there is one more trick that we should know. And it deals with this first example here. In this first example before, we started off by saying, oh, well, the sine of theta is just going to be, according to SOHCAHTOA, opposite over hypotenuse. That's just 12 over, we don't know the hypotenuse. Here's the last trick that I want to remind you of. Anytime you know 2 sides of a triangle, you can use the Pythagorean theorem to find the third. Pythagorean theorem says that a squared plus b squared equals c squared, where c is your hypotenuse and a and b are your other 2 legs. Hypotenuse, and these 2 are just your other 2 legs, or the other 2 side lengths. So let's take a look at example 1 again. We do know the two legs, but we don't know the hypotenuse. So let's plug it into the Pythagorean theorem. The theorem says that the first leg squared plus the second leg squared equals the third leg squared. Since 5 squared is 25 and 12 squared is 144, this means that that equals c squared, or 169 equals c squared. From there, to solve for c, our hypotenuse, we can just square root both sides. The square root of 169 is 13, so we know that our hypotenuse is 13. Nice. We can finish off our fraction. Sine of theta is opposite over hypotenuse, which is 12 over 3, or 13. If we're looking at cosine, it's the adjacent over hypotenuse. That's the ka in SOHCAHTOA. Well, the adjacent side here is the one next to the angle. That's 5. So it's 5 over our hypotenuse of 13. Then for tangent, which is opposite over adjacent, that's the TOA in SOHCAHTOA. The opposite we said was 12, the adjacent is 5, so it's 12 over 5. Easy. But it asked for all 6 trigonometric functions. So we also need cosecant, secant, and cotangent. I've got some good news for you, though. If you got the first 3, these are just the reciprocals, right? It just means that we can flip all of our responses. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. That's 13 over 12 instead of 12 over 13. The secant is going to be the hypotenuse over the adjacent. Originally, the adjacent over hypotenuse is 5/13, so this is 13/5. Finally, the cotangent is going to be adjacent over opposite instead of opposite over adjacent. So instead of it being 12 over 5, it's 5 over 12. Done. We have just found all 6 trigonometric functions. Now, from here, we have the following. Example 2 says, in a right triangle, theta is an acute angle, and the sine of theta is 4 over 7. We even drew you the diagram here, although even with just that information, we could build a triangle that has 4 over 7. Opposite is 4, hypotenuse is 7, and we could solve for the other side. But they gave it to us, which is nice. We just now need to evaluate the other 5. So I'll just write down sine of theta just for good record keeping. Sine of theta is 4 over 7, because it's opposite over hypotenuse. What's the cosine of theta? Well, that's the adjacent over the hypotenuse. The adjacent is the square root of 33, so it's the square root of 33 over 7. And our tangent is opposite over adjacent. The opposite is 4. The adjacent is 33, but hang on a second. Something doesn't look right about that one. Can we see what it is? We are not allowed to have radicals in the denominator. So how could we get rid of the square root of 33 in the denominator? Well, if we multiply it by the square root of 33, it should cancel out just to make 33 on the bottom. On the top, we would have 4 times the square root of 33. And we do want to check to see if the square root of 33 can be simplified. It can't in this case, though. But if I was to give you something like the square root of 16, or the square root of 32, or the square root of 72, we would have to simplify it. Let's see if we can find the other 3 trigonometric functions now. I'd like you to pause the video and see if you can find the cosecant of theta, the secant of theta, and the cotangent of theta. Try these out, and remember, no radicals in the denominator. Pause the video, and take a look back in a minute. All right, hopefully we had a chance to give this one a shot. Since the cosecant is the reciprocal of sine, instead of 4 over 7, it's 7 over 4. Similarly, with secant, it's the reciprocal of cosine. So where it was originally square root of 33 over 7, it's now 7 over the square root of 33. But, we've got a square root in the denominator, so we should multiply both the top and the bottom by the square root of 33, giving us 7 root 33 over 33. Finally, for cotangent, if the tangent was originally 4 over the square root of 33, or we could write it as this, we can just flip it to the square root of 33 over 4. Done. Those are the trigonometric functions. Let's flip the page. Now, this is very important. There were two types of triangles we learned about in geometry. They were called the special right triangles. There was the 30, 60, 90 right triangle, and there was the 45, 45, 90 right triangle. Here's the deal with these triangles. So the 30, 60, 90 right triangle looks like this. And the side lengths were always going to be proportional to each other in this way. If your shortest leg is x, your hypotenuse could be measured as 2x, and your other leg would be x times the square root of 3. So let's say I gave you a 30, 60, 90 triangle, named so because the angles are 30, 60, and 90. And let's say I told you that the shortest side is 7. We could then fill out the rest of these sides. 2x is 2 times 7, which is 14. And x root 3 is 7 root 3. Done. Pretty simple, right? Because of the way this triangle is, it means that any x value will give this proportion. In other words, the hypotenuse is always double the length of the opposite from 30 degrees. It's also going to be x root 3, which is adjacent to 30 degrees. So we have a rule that can actually help us here. For any 30-degree angle, we actually have a little list of what values we get. The opposite over hypotenuse, in other words, the sine, is 1 over 2. You see how we would get, for this one, the sine of 30 degrees would be opposite, which is 7, over hypotenuse, which is 14, which is just 1/2. That's how it's always going to work with a 30-degree angle. The sine of a 30-degree angle is always 1/2. Similarly, we can think about the cosine of that angle. What's the adjacent over the hypotenuse? Well, our adjacent is 7 root 3 over 14, or it could be just anything root 3 over whatever it is. Either way, when we simplify this, we get square root of 3 over 2. And we could go on, and on, showing how all of these things are related. Instead, I'll refer you to the chart. Sorry. The other special right triangle we learned about in geometry was a 45, 45, 90. This is when this angle and this angle were the same, and this is a 90-degree angle. What we learned there is the legs are x, the hypotenuse is x root 2. So similarly, if we take a look at 45 degrees, we can make any ratio. And lastly, we can do the same thing with 60 degrees. All this is to say, we have some options here for how we write these. However, these are nice shortcuts. If you can memorize them, you'll be golden. Another tip to help you memorize them is that to remember, sine and cosecant are just reciprocals. It's just flipped. Same with cosine and secant, tangent and cotangent. So if you can just remember this side of the table, you can just flip all these fractions and get this side of the table. Let's see if we can use this table to help us with example 3. Example 3 has us find a missing value of x. Ooh. Well, there's two ways to do it, and I'm going to show you both. The good news is we have an angle, and we have some sides to reference. As long as you have an angle, you can set up your trigonometric ratio. What ratio would deal with the adjacent side, so the side right next to 30 degrees, as well as the hypotenuse, which is 8? The only ratio that really makes sense here is the cosine, because the cosine is adjacent over hypotenuse. So we could say that the cosine of 30 degrees equals x over 8. And using both our methods for today, we're going to start here with the cosine of 30 equaling x over 8. For the first method, if you use your table, you can actually see exactly what the cosine of 30 is. According to the table, for a 30-degree angle, the cosine is the square root of 3 over 2. So we could rewrite this as the square root of 3 over 2 is cosine of 30, and that equals x over 8. From here, we just need to cross-multiply and simplify. This gives us 2x equals the square root of 3, 8 times the square root of 3, my bad. And to get rid of the 2 in front of the x, we can just divide both sides by 2. We get x equals 4 root 3, and this is an exact answer. So if you can use this table, do it. You'll get a more exact answer. If you don't know the table, it's okay. There's another method. The other method is to solve this algebraically. This is Algebra 2 after all. So how do we get x by itself? Well, we would just multiply both sides by 8. So we get that 8 times the cosine of 30, whatever that is, equals x. For these problems, I want to show you how you can plug them in your calculator. And it's relatively easy. In your calculator, the sine, cosine, tangent buttons are right here in a line. So if we're doing 8 cosine of 30, and press enter, we should get this number. Listen up. If you did not get this number, if you got something different, I need you to do me a favor. Go to Mode and go down to where it says Radian and Degree. You should be on degrees, because if you select radians, look at how weird your answer becomes. 1.234. That's not at all the same number. We're going to talk about radians in the next section, but for now, just remember, when we're talking about degrees, like a 30-degree angle, your calculator should be on degrees so it knows what you're talking about. Either way, we get 6.928 for x. So that's our x value. These are equivalent. It's just that this one we had to round a little bit. All right? Now let's put it to the test. We are now going to use our calculator, so we're going to use the second method, to solve a right triangle. Solving a right triangle means to find all the unknowns. Sides, and angles. So, we know there are 180 degrees in a triangle. We know that in a right triangle, we have one of the degrees is 90. Can we find the missing angle for this problem? Well, if 180 degrees is what we're starting with, but we know the 90 and we know the 28, if we do this, we should find our missing angle. 180 minus 90 minus 28, according to my calculator, is 62. So B equals 62 degrees. Nice. From here, we have a bit of freedom. We need to find these missing side lengths. Whichever one we start with and whatever ratio we use is sort of up to us. Let me give you an example. Let's say I wanted to find side A, but all I know is the 15 and the 28 degrees. Well then, I don't need to take a look at C or this other angle. All I need to do is set up a ratio that has the opposite side and the adjacent side. What ratio is that? That's tangent. So can't we just set up the tangent of 28 degrees equals, the opposite side would be A, the adjacent side is given to us as 15. Couldn't I just do the same thing I did in the last problem? The answer is absolutely. Multiply both sides by 15. And 15 times the tangent of 28 degrees is 7.975, which I'm going to shorten as 7.98. Cool. Could I have done this a different way? Absolutely. I also know the 62-degree angle, right? So I could do opposite is 15 over adjacent is A and solve for A that way. Ho-ho. You have relative freedom for how you do these problems. As long as you show your work, doesn't matter what ratio you use, or even if you don't use a ratio. For instance, now that we know two sides approximately, we could just use the Pythagorean theorem to solve for C. I'm not going to do that here. I'm going to use another ratio because I think we need the practice, but you could. So let's use the 28-degree angle again. And I want to use the 15 side, just because that's an exact number and it's a little nicer than doing 7.97564. What ratio involves the adjacent side to that 28-degree angle and the hypotenuse? Well, that's cosine. The cosine of 28 degrees is equal to the adjacent, which is 15, over the hypotenuse, which is C. Now, you could go and solve this relatively algebraically, but I also wanted to remind you of a little trick I taught you a couple units back in Unit 7. If you ever have something that's not a fraction equaling something that is a fraction, and you're trying to get your variable out of that denominator, you're allowed to just swap the two sides. C equals 15 over the cosine of 28. And if you don't believe me, go ahead and solve it by hand. You'll get to the same point. If I go in my calculator and I type in 15 over the cosine of 28, I get about 17. It's like 16.99. So our C value is about 16.99. Done. This triangle is solved. It's got all of its sides. It's got all of its angles. Next up, we have these two word problems. And these will be the last ones we do for the notes today. So let's say we're hiking near a canyon. While standing at A, so we're standing right here, we measure an angle of 90 degrees between B and C as shown. It's not shown. It's really kind of hard to see, actually. There's a little right angle marking here. So angle A is a right angle. We walk to B, and we measure an angle or a distance of 2 miles. And we're trying to figure out how wide the canyon is just based on the fact that there is 2 miles and that the angle between B and C is 76 degrees. How do we do it? Well, what we're really trying to find is CA, or AC. That's our hypotenuse. So we really got to ask ourselves, what ratio involves this angle, this side, and our hypotenuse? Well, since 2 is adjacent to 76 degrees, oh, I apologize, y'all. This is not the hypotenuse. My bad. The hypotenuse would be BC. That was just straight up incorrect on my part. This would be another leg. In other words, this would be like side B. So what involves the 2 legs? Well, that one's a little easier to manage. That's tangent. The tangent of 76 degrees equals the opposite over adjacent. Well, the opposite is AC, so that's our unknown. We'll call that AC. And the adjacent, the one next to this angle, is 2. So the tangent of 76 degrees equals line segment AC over 2. To solve this, we could just multiply by 2 on both sides to get 2 times the tangent of 76 degrees equals that line segment AC, the length of it. And if I do this on my calculator, 2 times the tangent of 76 degrees is 8.02. So the canyon, in other words AC, is around 8.02 miles. Fantastic. From here, we can take a look at example 6, and this is one where I recommend drawing a diagram. I usually recommend drawing a diagram for these word problems. So we've got a parasailer this time. So he's got his little parachute, and he's holding on for dear life. They're attached to a boat with a rope that's 72 feet long. So here's my expertly crafted boat. We've got a rope here connected to the paraglider that's 72 feet. It then says the angle of elevation from the boat to the parasailer is 28 degrees. The angle of elevation, or the angle of incline, is the angle from the flat ground to whatever line was created. In this case, we would say that this is the angle of elevation. And we've got to estimate the parasailer's height. One thing we could do is we could finish making this triangle. So if we finish this triangle, here's like sort of perpendicular to the ocean, and here's down to where the parasailer would be. That's a right triangle, right? As long as it's a right triangle, we can do right triangle trigonometry. Again, we're trying to find this. I'm going to call this variable h for height. How do we do it? Well, h is the opposite side from the angle, and 72 is the hypotenuse. So what trigonometric function has to deal with the opposite and hypotenuse? That's the sine. So the sine of 28 degrees equals h, which is our opposite, over 72, which is our hypotenuse. That means that if I multiplied by 72 on both sides, 72 sine of 28 degrees is going to be our height. Once again, we bust out the trusty calculator. Oops. 72 sine of 28 is 33.80. So the height is around 33.8 feet. Done. you so much, everybody. That concludes our notes for today. I hope you have a fantastic rest of your day. Take care.